later. Okay. Well, the second, the first operation is corresponds to multiplying the matrix we get from C by another matrix which has just one off-diagonal element. Well, formally speaking, here we have the way it's written. We have an element of pi 1, but then we can get a linear combination of elements of pi 1 in the same way. So here we may just as well realize any element of the group ring. Now the second operation on the level of matrices should be multiplication by an element of G, and it's realizable as a change of base point. Now let's see what happens when we change the base point. What happens on the level of on the level of chain complexes? Are there any ideas? Change of base point. Change of the base point upstairs.
Upstairs.
This means we in order to have a preferred basis, we need to have a base point in W. In W in the universal cover of W. Sorry. So once I haven't mentioned the following thing. if we have a handle decomposition of W, we also have a handle decomposition of the universal cover, which is
I just don't understand what you mean. You just can choose any path. Why are you changing base point? You can just change any path going to any handle.
Well, I didn't mention.
This was the multiplication.
I didn't mention the following thing. Suppose we have a handle and a path downstairs, and a choice of a base point upstairs. Then we get a handle upstairs. And by choosing a different path, by choosing different paths, we get all possible handles above the given handle downstairs.
You mean it is important on which handles you are just taking the path? Along which handles you are just...
I want couples handle path to correspond to something geometric. To what? Well, one obvious thing is a handle without paths upstairs.
Upstairs on the cover.
On the universal in the universal cover. But in order to get this handle, I need a base point upstairs, which I didn't mention.
On the universal cover.
In the universal cover, which is inside the preimage of a given handle downstairs. But of course, the choice of this base point upstairs is completely arbitrary. So I need to be able to relate the chain complexes which correspond to different base points. And
this is just multiplying all elements by the same.
the claim is that the differential remains the same, except that it gets multiplied by an element of G. And the last operation is is adding a trivial summand or subtracting. And this is realizable by handle creation or annihilation. And there are well, there are two things which we need to take into account, which are not there in the simply connected case. Difficulty number one is that
to choose a path.
If we have two intersection points downstairs with opposite sign, what do? We connect them on one sphere, and then we connect them on the other sphere. And the Whitney trick tells us that they cancel. Why? Because there is a Whitney disk which bounds the two paths, one in one sphere and the other in the other sphere. Well, in the non-simply connected case, the result is not necessarily the composite of the two paths is not necessarily contractible. So difficulty number one. Suppose we have two intersection points, and the intersection points of the attaching sphere of some handle and the bell sphere of some other handle. Now, they do not necessarily cancel, but they do cancel if so suppose suppose the signs are opposite and the corresponding group elements are the same. Then then the path that we use in before we apply the Whitney trick is contractible. So after we get a direct sum of the trivial complexes, we are able to eliminate pairs of handles with opposite intersection points, basically using the same procedure as in the simply connected case. And another difficulty is handle trading. Recall that to do the Whitney trick, we need to assume that all handles have index at least 2, which means the spheres that we intersect have dimension at least 2. In particular, this picture is not realistic because the spheres have dimension 1. And to make sure we have all spheres of dimension 2 or higher, we need to get rid of the 0 handles and 1 handles. Well, the 0 handles are easy. They are handled in the same way as in the simply connected case, but we need to understand what happens with 1 handles. And let's see what happens with.
But still, on the previous step, you have specific choice. You have specific assumption on cancel points.
Yes, the extra assumption is that the group elements constructed using both intersection points must be the same.
Yes.
Which is what allows us to conclude that this loop is contractible.
Yeah, but it cannot be cancelled by some. Yeah, but you have to reduce to this equation. Yes, we have. I just said without proof that if the torsion is 0, then using operations of these 3 types, we can transform a complex into a sum of trivial complexes. We can transform our chain complex into a sum of the trivial complexes, meaning a sum of complexes of this type. So far, this is an algebraic result, and we want to. Oh, by the way, I'm. Hold on, I'm. Yeah, but here, I mean, there is some specific choice.
Yes. basically adding or removing. Adding is straightforward, but removing requires this argument. This is a justification of the fact that we are allowed to remove copies of this.
Yes, I understand, but I mean, on the previous step we had the claim that the signature is 0, so the intersection index is 0. So then it implies that the points combine to points of opposite side.
Mm.
I mean,
yes.
They come into the test. So here we should have the same kind of results. So if the intersection number is, so if the torsion is 0.
Yes. So suppose we have lots of intersection points, and they sum up to 0
Yes.
as elements of Z pi 1. Then we assume that all intersections are transversal, so each intersection point contributes.
So it has one specific element as a multiple
yes.
fundamental group as a
yes, with some sign.
Yes.
And then we
so they cancel. Yes. Just the element.
We just for each point we choose a point with the same element of the group and opposite contribution, and then we apply the Whitney trick. But before we are allowed to do that, we must get rid of handles of index 0 and 1, and similarly of handles of index top minus 1. Well, let's see what happens when we try to get rid of one handles. Well, obviously, one handles cannot in general be cancelled, but we are in a particular case when we have an inclusion of M0 into W, which is a homotype equivalence. So on the level of pi 1, it's an isomorphism, and we don't need to worry about the pi 1s being different. So what do we do? Basically, all I can think of is working upstairs, but pi 1 equivariantly. What does this mean? This means suppose we have a one handle. Suppose we have no 0 handles. Then we have then suppose we have some number of 1 handles downstairs. we don't have any zero handles, so the preimage of a one handle downstairs is some number of one handles upstairs. Upstairs, they're all they're all contractible because upstairs we have a manifold which is W tilde, which is simply connected. And then we choose one of them and choose a disk which bounds the core plus plus something. And then we take all pi1 translations of this disk, and then we do the same thing we did in the simply connected case, but pi1 equivalently. Does this make sense? What is it?
Why can't we, for example, do it first about this just the same way? For example, the ball field universal. For example, do the bit tree in the universal for the disk number one.
Sorry.
Can we do this procedure again?
Well.
Instead of what we said.
Yes, so suppose we have a one handle so the preimage of a one handle H1 is is a disjoint union of the preimages of is the disjoint union of the copies of some preimage of this handle. Now this W tilde is simply connected, so we can choose a
yes, so in order to start handle trading, you have to choose the
I have to choose
path along your handle. Just it should be contractible.
Yes, it should be contractible in W tilde. Well, yes, I choose I choose a disk which bounds the core of the one handle and well, which bounds a loop that goes from the base point to one endpoint of the one handle, then goes along the core to the other point to the other endpoint of the one handle, and then returns to the base point, which is what we did in the H-cobordism case. So I choose any loop like that in W tilde.
Yeah, but if you do like that, I mean, why should you do it equivalently? You can just project the.
Yes, yes, but then I want to say that this loop bounds a disk.
Upstairs.
Well, somewhere. upstairs,
This simply can
upstairs.
then you have a disk.
Yes, upstairs I have a disk. Downstairs, downstairs. Yes, yes.
Неудачно выбирая путь снизу, ты просто как бы у тебя путь не замкнется. Но если у тебя путь наверху, ты
да, значит, и более того, он там даже ограничивает диск, но потом нам все равно понадобится в какой-то момент односвязность.
Так а где? Если ты наверху ограничил диск.
Значит, да, я наверху ограничил диск и, ну, давай подумаем. Значит, я наверху ограничил диск, и мне хочется, чтобы этот диск спроецировался вниз однозначно.
Ну, так он в смысле однозначно?
Ну, там без...
да, вот это...
без пересечения.
Без самонаезда.
Да.
Ну, да.
But another way to argue would be to say that the image of this loop is obviously a loop, and it's it's contractible upstairs, so it must be contractible downstairs, and this means that it bounds a disk. Why? Because the dimension is high enough.
Then the problem, as you have stated, that this disk, if it is projected, it can have self-intersection.
I project the loop first, and then take a bounding disk.
Yeah, but it can happen that the disk has to bound the loop.
And then if the dimension is high enough, the bounding disk can be assumed embedded. Let's see. Does this mean that the difficulty doesn't arise?
Yes.
Let's think a little. Let's think. Well, the reason, the only reason this may break down is when there are zero handles. But because the only thing we're not able to find such a loop is when the two endpoints of the one handle are inside different connected components. But we assume that there aren't any zero handles, so this problem is not there. So we have gamma tilde inside W tilde, and then this gamma tilde projects to a loop. Gamma inside W, which bounds a disk. Okay, does so it looks like this difficulty is well relatively easy to sort out.
Moment is that why your handle is I mean why your handle shouldn't be cut on your cover.
Well, yes.
I mean, since it is a silent, I suppose you have.
Yes. So so why the two endpoints of the one handle?
Почему твоя ручка, она не развернется в неручку? Почему ты утверждаешь, что у тебя есть одна связанная накрывающая? Ты именно приклеиваешь ручку, а то просто может быть так оказаться, что у тебя цилиндр, нужно разрезать и развернуть, сам себя должен поднакрыть.
Когда мы проходим через критическую точку функции, у нас приклеивается ручка индекса такого-то. Теперь, когда мы берем функцию, функцию наверху, которая получена из функции снизу, локально происходит абсолютно идентичные вещи. Что могло бы случиться? Это, один ручка могла бы соединить две связанных компонента различных. Но если мы уже избавились от 0 ручек, то такого не происходит. Okay, so the handle trading trick also works, and then basically the rest is the same as in the H-cobordism case. There are plenty of things which we didn't really prove, but I hopefully explained the main differences which are present in the non-simply connected case. Are there any questions? Okay. Now, where next? Well, the next thing we want to discuss is surgery theory. Let's let's ask one question as an example, and then we'll make this question more precise as we go along. Well, suppose we have we have a smooth manifold and well, let's assume this manifold compact, and suppose we have a continuous map from M to X, which is to begin with, let's not assume anything on X. And on F. The question is, when is there a smooth manifold M prime cobordant to M and a homotype equivalence from M prime to X? In other words, which homotype type, what are the homotype types which have smooth manifolds as representatives? The way this is stated, the way I've stated all this, I don't require anything on F, which is strange, because why bother talking about F if I don't include it here? So let me. Let me add here that the homotype equivalence should be cobordant to F. What is this supposed to mean? Well, I will give a more technical definition shortly, but what I want is to have a map capital F from F to X such that W is a cobordism from M to M prime, so I have W, the boundary of W equal M disjoint M prime. And on M, I want this F to coincide with small f, which I'm given. And on M prime, I want capital F to be F prime, which is a homotype equivalence I'm after. This is the sort of questions we want to be able to answer. And we will mainly assume everything simply connected. Why? As we saw in the H cobordism case, the ideas are in the simply connected case and the non-simply connected case are the same, but the non-simply connected case is technically more difficult. Well, the same happens for questions of this type. In the simply connected case, the answers are tractable and quite explicit. In the non-simply connected case, there are extra complications which are again possible to handle, but anyway, let's do the simply connected case first, because the main geometric ideas are already present in this case. And the non-simply connected case is well, to be honest, it's quite complicated. So I would suggest we just don't mention it at all. Well, of course, I'll give a couple of references, but then unless you really need it for something, there's no point in talking about it here in class. Anyway, Well, the first obvious obstruction for there to be such a homotype equivalence is that X should be should have a Poincare duality. Now. Let's try to formulate the Poincare duality in a homotype invariant way. How would you state the Poincare duality in a homotype invariant way? So suppose I want to define a Poincare duality space of dimension n. What do I do? I want something which would be homotype invariant. Meaning I would like to have if two spaces are Poincare duality of the same dimension, then if one space is a Poincare duality space of dimension n, I want every homotype equivalent space to be a Poincare duality space of the same dimension n. What do I do? Well, let's first assume that phi 1 is 0. Then the answer is pretty straightforward. What's the answer? Are there any guesses?
Just like manifolds, the homology of degree D equals the homology of dimension minus.
Yes, but we want to have not only an isomorphism between homology and cohomology. We want this isomorphism to be given by the same formula, which would be ideally a homotype invariant. So And one way to do this would be to require that there should be an x inside. Well, I don't really. Well, let me erase this. This is a consequence. Let me assume here that x is path connected. Then, if I have an isomorphism from hi to h lower n minus I, by taking I equals 0, I get hn equals n. Does everyone understand what this is? Okay, now I've just said we will not worry about the simply connected case, but let's just to just today, let's see how this very simple notion generalizes to the non-simply connected case. What do you think? How can I define Poincare duality spaces in the non-simply connected case? What do you think? Well, there aren't any surprises here. So, in general, we require that there should be a local system L of rank 1 and the class X, which has basically the same property.
Это все-таки сказать, что просто не гарантированно в моем случае, а не
Well, so this thing includes L as which may or may not be trivial.
Yes, but I do not see what is the problem on having P1
Well,
I mean, we still have a Poincare duality.
Yes, but with this, so if for example,
of course, if it is not oriented and you want to have the coefficients in Z, not in Z2, then you should have the local system.
well, for example, if I take this as the definition in the non-simply connected case, then RP2 will not be a Poincare duality space, which is sort of which is not exactly what we want, because it's a manifold. So we want to include an extra yes, but from the homotopy point of view, the problem with orientability is a problem with pi1. So if we want to have a homotopy invariant definition, we need to include a local system, or at least that's the way I see it. Maybe maybe I'm wrong.
I'm not against local system, but so now it's clear.
So here we have HIX.
I mean, you do not want to play just so you want them to play to explain what is being orientable. So you want to include the non-orientability in some homotopic notion, which is now so it can be plugged in P1. Yeah?
Yes. So I require that this map should be an isomorphism for every local system M. One X. And with this definition, all manifolds, all smooth manifolds become Poincare duality spaces, whether they are orientable or not. And apart from this, we will need Poincare duality pairs. Which is very similar, very similar to what happens for spaces. We just consider we generalize the Poincare Lefschetz duality for to pairs. So suppose we have suppose we have a CW pair, it's a Poincare duality pair. Well, again, Poincare duality pair of dimension n. If there exists a fundamental class, by the way, where should this x live? Are there any suggestions? Say again? Yes, in Hn xy such that capping with the fundamental class gives me two isomorphisms, which one of which goes from the cohomology to the relative homology, and the other one from the relative cohomology to the homology. Okay, now why do we need pairs? Well, it's mainly a question of convenience. We will quite often want to glue a Poincare duality space out of smaller Poincare duality spaces, and it's a lot easier if we allow arbitrary pairs than when we consider just Poincare duality spaces. Okay, now the next step is to state some of the main theorems of surgery theory, and the question is, do we want to do this today, or do we want to do this next time?
Before that, what is the second map here? I think that should be Hn minus I minus 1 of this. Can you explain what it is?
Hn minus I
Minus 1, because
minus 1.
You are capping with x, and then you are taking the exact sequence of pairs, right? So it must be Hn minus I minus 1.
Let's see. Cohomology is basically if I take the cap of two things, the result has degree which is equal to the homological degree minus the cohomological degree. So the homological degree is n, the cohomological degree is I, so it's n minus I in both cases.
No, in the second case, when you cap with x, you will go to the n minus I homology of pairs, like x and y. So
No. Let's try to remember. So we well, first of all, we have the cup product. Which goes from the relative homology of mod A, tensor the relative cohomology mod something, tensor the relative cohomology mod something else to the relative cohomology mod the union. This is straightforward. But then for the cap product, we have something similar, but not exactly the same. In particular, I have, if I take in this formula, I can take B equal the empty set and A equal Y. Then I get the relative homology tensor, the relative cohomology tensor, the relative homology to the absolute homology. Or I can do vice versa. I can take A empty and B equal Y, and then I get the other map. Well, let's see where this comes from. Suppose I have
just because cohomology are chains that are vanishing on.
Yes.
On
so
this is annihilated.
So this is given by co-chains which are zero on A, and these are basically chains which are defined up to chains from here, from the union. When I take the cap product, if I have a chain from A, the result is zero because the co-chain is zero. And if I take a chain from B, well, it doesn't matter anyway because here I have relative chains. For more details, you could have a look at what Hatcher says when he talks about the cap product. Okay, now and these are two isomorphisms, and they are different. They're not. They're the same when y is empty, but otherwise they're not the same. Okay, now do we want to start talking about surgery now, or do we want to do this next time?
Since you formulate the theorems, you can still formulate them.
Okay. I'll.
And next time we shall.
Well, the problem is no, the theorem I wanted to formulate is long. The question is, do you want to hear? It's not. It's not an easy. No, let's do it next time, because there's if I state the theorem. If I state the theorem today, I or someone else will have to repeat it next time anyway, because what's the point in stating, in proving the theorem if everyone, if no one remembers what the theorem says?
Ты не с тем связался. Вот, никогда не поздно повторить. И не вредно.
Нет, можно сформулировать, нет, значит, в следующий раз все равно все придется повторять. Okay, well, I'll state one. To begin with, I want to state not a theorem, but a definition. Which we will need to state any of the theorems. Well, first of all, I will state a few things, and they are mostly self-explanatory. But let's nevertheless write them down and see if everyone. I'm sorry. I want to define a Buddhism between f and f prime, where f and f prime are maps of pairs. Well, here M prime are smooth manifolds. X, Y is a Poincare duality pair. F prime are continuous maps, and we want to define a Buddhism between two maps FF prime. Well, it's well, since we have an extra manifold so since we have a Buddhism between something which is not a closed manifold and but a manifold with boundary, let's just specify what happens on the boundary. So we define a Buddhism between f and f prime as a map from w dw to xy such that dw is w is again a smooth manifold, but dw is M prime and another part U, where du is the same as dm disjoint with dm prime. Let me draw a picture. Okay, so this is M. This is dm. This is n prime. dm prime, and this is u. And what is this thing doing here? Well, we'll shortly see. This is a disk which contains m and m prime, and such that the boundaries inside the boundary and so on. Anyway, to begin with, ignore the disk. Let's just focus on m and delta m and so on. Well, let me put a disjoint union here. Because otherwise it's not well. And the last union is not disjoint. So delta u is the same as delta m disjoint with delta m prime. Okay, now now we need to define normal maps. What are these? Well, suppose we have a Poincare duality pair and a manifold, a smooth manifold with boundary. What is a normal map from the manifold to the Poincare duality pair? Well, it's couples. Let's see, not couples. I don't want couples. What do I want?
You should have bundle elements.
Well, yes. So Xi is a bundle, and well, let me say tuples. It's the safest option. F. So I want to have I want to have well, first of all, I want to have a map from MDM to XY. Now, second of all, I want to have a vector bundle. Third of all, I want to have a fiber-wise map of bundles which covers F. Now, well, psi is just some vector bundle on X. What is new? Oh, well, new is the normal bundle of some embedding of the manifold M into the disk such that the boundary delta M goes to the boundary and well, basically, this diagram is Cartesian, meaning M intersected with the boundary is the boundary of M, and the intersection is transversal. In particular, the normal bundle of M restricted to the boundary delta M is the same as the normal bundle of the boundary inside the sphere. Okay, now does this make sense to everyone? Well, we have defined normal maps, and we have defined Bordisms. Now we need to define normal Bordisms. What are these? Well, these are Bordisms which are normal maps. And I think now we have all ingredients which we need to state the theorem, and very briefly, the theorem says the following thing. Suppose I have a normal map, which is a homotopy equivalence on this component, on the boundary. Then I can associate to this map an element of one of the following groups: Z0, Z by 2, or 0, depending on whether the dimension mod 4 is 0, 1, 2, or 3. And the normal map is normally Borden to a homotopy equivalence, meaning to map M prime X, which is a homotopy equivalence, if and only if the invariant of the initial map is 0. In particular, if Y is empty, then the answer is that there aren't any obstructions, because the invariant takes place in the 0 group. We'll talk about this in more detail next time, and while we're at it, I think this is another another topic for a talk. I think I've been speaking for long enough, and everyone's grown tired of me. So it's time for other people to say something as well. Next time we will state the main technical results of surgery theory, and we will prove some other results using those technical results. Okay. Are there any questions?
Why did you write -1?
Yes, you're absolutely right. It's supposed to be. Yes, so yes, I was. Yes, I was thinking about the sphere. So this is where -1 came from. Are there any more questions? Okay, well, then I think this is it. There's a seminar which starts in 10 minutes, I think.